Up until the latter half of the 17th century, there were two predominant theories about how fast light can travel. The first and most popular of the two was one supported heavily by René Descartes, that light travels at an infinite speed. The second and less popular theory was that light travels at a finite speed, but is and always will be too fast to detect or measure. In 1607, Galileo tried to measure the speed of light with the aid of an passed, faraway assistant. This assistant stood on a hilltop, and both of them had a covered lamp. Galileo would uncover this lamp, and when his assistant saw the light from his lamp, he uncovered his. Galileo tried to calculate the time that passed from his uncovering of the lamp to his seeing the lamp of his assistant, while taking into account the time it took for his assistant to uncover the lamp. Galileo could not reach any discernible time, and therefore concluded that the speed of light is either infinite or too fast for anyone to be able to measure, not taking either side of the opposing theories. This debate would rage on for around another century, but the first evidence of light having a finite speed would come in 1670, when a Danish astronomer would have a brilliant burst of intuition that would lead to the first calculation of the speed of light. Ole Rømer was born in Aarhus, Denmark in 1644. Little is known about Rømer's early life, other than the fact that he enrolled in the University of Copenhagen in 1662 at 18 years old. His mentor at Copenhagen was Rasmus Bartholin, a Danish physician who discovered the double refraction of light in calcite. In fact, Bartholin made his key discovery in 1668 while Rømer was living with him in his house. Bartholin, while at Copenhagen, also had the job of preparing Tycho Brahe's astronomy papers for publication, and therefore Rømer had the opportunity to learn advanced mathematics and astronomy from Brahe's papers. In 1672, Rømer moved to Paris to work at the new observatory at the Royal Academy of Sciences. He spent 9 years there focusing specifically on the moons of Jupiter. After making 3 years' worth of observations of Jupiter's innermost moon, Io, he noticed something peculiar about its orbit. Rømer had been using a pendulum clock invented by Christian Huygens 18 years earlier to measure the time it took for Io to complete a full orbit around Jupiter, and noticed that when Earth was moving away from Jupiter, Io's orbit was 13 seconds longer than it was when Earth was moving towards Jupiter. There were two main conclusions that Rømer could come to after seeing this phenomenon. The first is that Io's orbit is slightly erratic, and these slight variations of the orbit are perfectly synced to Earth moving away from and towards Jupiter. The second was that the speed of light is finite and is taking more time to reach Earth from Jupiter when Earth is moving away from it. To try and figure out which of the two possibilities was correct, Rømer began studying eclipses of Io as the moon passed behind Jupiter. Later that year, Rømer read his results to the Science Academy, where he explained his results using this diagram here as follows. When Earth is at point L in its orbit around the Sun, Io is entering its eclipse behind Jupiter at point C. When it exits its eclipse at point D, Earth is now at point K in its orbit. The light coming from Io would have had to travel this extra distance to reach point K instead of point L, so Rømer would just need to calculate how much later Io is observed emerging from its eclipse as compared to what was predicted through years of observation of its orbit. Rømer found this delayed time to be about 10 minutes. Combining this with a calculated value of Earth's orbital diameter at the time, which was done so in 1671 by the director of the Paris Observatory, Giovanni Domenico Cassini, linked us an additional geometry, Rømer came to the conclusion that light travels at approximately 230 million meters per second, which is about 3/4 of the currently accepted value. Most of the error in Rømer's calculations is attributed to two correlated measurements. The first being the calculated time it would take light to cross the entire Earth's orbital diameter, and this calculation turned out to be 38% too large. The second was the calculated diameter of Earth's orbit itself, done by Cassini, and this calculation was 7% too small. Römer published his results in a short paper entitled Demonstration Concerning the Discovery of the Movement of Light, the next year in 1676. About 50 years after Römer's work brought to light the first experimental evidence of its finite speed, English astronomer James Bradley refined it even further using an entirely different method, the parallax method. Bradley's intention was not to calculate the speed of light, but rather to find evidence of Earth's motion around the Sun by measuring the annual stellar parallax. Bradley figured that if he were to measure the change in angles of the stars in the sky over a 6-month period, it would further validate the theory of Earth rotating around the Sunday. Römer himself also tried to do this years before, but angle shifts were so small that he was unable to detect them. Bradley also was unable to find any evidence of an annual stellar parallax, but he did notice a different phenomenon, a parallax shift over a 3-day period in a different direction than predicted. With some genius insight, Bradley determined that these weird star shifts in the sky were due to Earth's motion relative to the speed of light in a phenomenon known as the aberration of light. When Earth moves into a path of light emitted from a star, it appears to be coming from a different spot in the night sky than it really is. The discovery of the aberration of light by Bradley not only provided the first direct evidence that the Earth is moving around the Sun, but also allowed him to calculate the speed of light through geometry. Quite precisely, he determined that light speed is approximately 295 million meters per second, which is off by only 2%, and also determined that light from the Sunday takes approximately 8 minutes and 12 seconds to reach Earth. The evidence provided by Bradley was crucial in determining that light travels at a finite speed. There was a lot of opposition to Römer's conclusions after his initial publication, led mainly by Cassini himself, who still believed that light speed was infinite. He believed that these weird anomalies in Io's orbit were due to the orbit itself and not because of light. Cassini had tried to find evidence of a finite speed of light earlier in his career as well, and through the same methods as Römer, but when he didn't find any such anomalies in the other 3 orbits of Jupiter's moons, he adopted the infinite light speed theory and held it to his grave. Bradley provided further evidence that Römer was correct in his conclusions, and other astronomers who came after Bradley further refined his results. In 1809, French astronomer Jean-Baptiste Delambre used a century's worth of calculations of Io's orbit to further refine the speed of light to roughly 300 million meters per second. Up until this point, all of the measurements of the speed of light had been made through observations of celestial bodies. No one had yet made any terrestrial measurements of light, for no one had a successful experiment to try and measure it, or if they did, they didn't have the technology to manifest that experiment into reality. Once the first celestial measurements of the speed of light were made, though, many scientists realized to what degree of velocity they were working with regarding light, and therefore realized the grand scale at which they needed to make an experimental apparatus. French scientist Armand Hippolyte Fizeau was the first to successfully make such an apparatus, and subsequently measured the speed of light based off of it traveling on Earth and Earth alone. Fizeau's 1849 setup went as follows. He used 2 hills with a distance of 8 kilometers between them. On the top of one hill, he placed a toothed wheel with a light source behind it, and on the second hilltop, he placed a mirror. He then began rotating the wheel so that the light that bounced off the mirror would return and be seen as a series of pulses. The returning light would be seen when it made it through the grooves of the tooth wheel and reached the observer, and wouldn't be seen when it hit the teeth of the wheel, which blocked it from returning to the observer. Fizeau then began to speed up the wheel's rotation, spinning it faster and faster until the wheel reached the speed at which all light let through a counter. Single groove ends up hitting a tooth of the wheel upon its return, which means that the observer would see no light whatsoever. Then, Fizeau used the known values for the rotational speed of the wheel, the number of teeth on the wheel, and the distance to the mirror to calculate the speed of light. His calculations yielded a value only about 5% too high at 315 million meters per second. Interestingly enough, at exactly the same time, another French physicist named Léon Foucault was independently devising a very similar apparatus, but with some slight differences. Foucault's setup also included rotation and mirrors, but in this case, the rotating device wasn't a toothed wheel, but rather another mirror. Light would travel from a source to the rotating mirror, bounce off of it, hit the fixed mirror, then return to the rotating mirror, and finally, back to the observer. The rotating mirror spun at a speed fast enough so that when the light returned to the observer, it was observed at a different spot relative to the source of light. Knowing the distances to each mirror, the speed at which the mirror rotated, and the angle of reflection, Foucault was able to calculate the speed of light to be roughly 298 million meters per second, which is extremely close to today's accepted value. Foucault announced his results 1 year after that of Fizeau, adding to the evidence pool of the finite speed of light and further refining its elusive true value. Most of the measurements of the speed of light up to this point have been close to accurate with 5% or less error, but they have not been all that precise. Most of the values round off to the nearest million meters per second, and filling in these zeros would require much more precision. This technology would not come until the 20th century and would come at the hands of a Prussian-American physicist by the name of Albert Michelson. Albert Michelson is known more famously for his 1887 experiment with Edward Morley and Palman, known as the Michelson-Morley experiment. It is the most famous deserting experiment in all of physics and provided strong evidence that there is no luminiferous ether, a supposed medium that hypothetically acted as a carrier for light waves. I covered this experiment in a previous video that I will link in the description if you are interested. The Michelson-Morley experiment itself operated through comparing the speed of light at different angles. Michelson was a pioneer at precision instruments for measuring the speed of light, and had been brainstorming ideas of how to refine its measurement since he was a Navy officer in 1869. He started with trying to find ways to improve Foucault's rotating mirror setup using better optics technology and expanding the distance at which the light would travel during the experiments. In 1879, he would reach a value for C of 299,910 m/s, plus or minus 50,000 m/s. While in the Navy, Michelson took mentorship under Simon Newcomb, better funding under Newcomb. Together through the years, they refined their measurement to 299,853,000 m/s, plus or minus 60,000 m/s. Still, even with a more precise measurement, Michelson was not satisfied. 33 years after the Michelson-Morley experiment in 1920, Albert began planning a new experiment that would measure light from the Mount Wilson Observatory in Los Angeles, California, to Lookout Mountain, roughly 22 miles away. Still using the same tactic employed by Foucault 70 years prior, and with the help of a 2-year-long process of measuring the baseline from the Bermudas, United States Coast and Geodetic Survey (UTANSID), Michelson reached a value for the speed of light of 299,796,000 m/s, with an error of only 4,000 m/s. This still was not the last attempt by Michelson to refine his calculated value for C further. There were some sources of error with his lookout experiment. The first was an earthquake that happened in 1925 in Santa Barbara while the Geodetic Survey was still underway. This earthquake compromised the baseline somewhat, and coupled with blurry images caused by the haze of the LA atmosphere due to forest fires, it's understandable that Michelson was still not satisfied with his measurements. His next and final effort would continue for the rest of his life and wouldn't finish until after his death. For this final attempt, he collaborated with Francis G. Pease and Fred Pearson, and in 1929 they invented a new and clever device. This device was essentially a tube 1.6 kilometers, or 1 mile long and 1 meter wide, Perhaps the most impressive aspect of this tube was not its size, but the fact that the entire thing was made to be almost a perfect vacuum. Michelson, frustrated with the haze affecting his measurements in the previous years, wanted the atmosphere to have absolutely no effect whatsoever on his next measurements. Inside the tube were a series of mirrors that reflected a light source, successively upwards of over 10 times. This setup was able to extend the light path inside the tube from 1.6 kilometers to just over 8 before it returned to the rotating mirror and then to the observer to measure the angle of deflection. The three scientists planned a series of 233 measurements throughout the course of several years to get the most precise measurement they could. Unfortunately, though, Michelson died in 1931 after only 36 of those measurements were made. The mile-long tube was not immune to air either. Since the trio was still in California, it was still prone to earthquakes, which would shift parts of the tube at times. It was in constant need of maintenance due to that, and also due to condensation issues affecting the visibility of light during their experiments. Regardless, the results were published in 1935, 4 years after Michelson's death, by Pease and Pearson, with a measurement for the speed of light of 299,744,000 pesh, with an error of 11,000 m/s. Since the 1935 calculation, the deployment speed of light has been refined further to 299,792,458 m/s. It's astounding how well the rotating mirror method worked and how it was the primary method of calculations up until about 1950, when the cavity resonator method was used by Essen and Gordon Schmidt. In 1983, the value of the speed of light was set as an official SI unit, and the definition of the meter was changed to the distance light travels in 1,299,792,458 of a second. This means that today, measuring light does not impact the accepted value of the speed of light. Rather further, refines the definition of the meter as more and more precise measurements are made. The speed of light in a vacuum is an incredibly fast speed relative to us, but compared to the scale of the universe is incredibly slow. It's our universal speed limit, and traveling at that speed is a prime example of pushing relativity to its limits. The sheer fact that scientists in the 17th century were able to take what seemed infinite to them before and turn it into a quantifiable value is beyond remarkable. Thanks to centuries' worth of innovation and the work of many brilliant scientists, our understanding of light has grown significantly along with the fundamental limits that lie within our universe. If you enjoyed this video, please consider liking and subscribing. Click here if you want to see more scientific progress made during this time. Thank you for watching, and I will see you in the next video.